In this short screencast, I would like to review a few things about electromagnetic radiation, electromagnetic waves. We talked about some of this back when we did our chapter on light. First of all electromagnetic waves travel in a vacuum with the speed of light. We use the letter C for the speed of light. It's a special designation as opposed to the more generic V for the velocity of other things. But in both cases, the product of the frequency times the wavelength equals the speed, whether it's a water wave or a sound wave, or especially in this particular part of the chapter, an electromagnetic wave, including visible light. This kind of information and understanding that there was more to light than just visible light was developed through very interesting experiments during the 19th century. And a couple of people, especially James Clerk Maxwell, a dynamic Christian man, wonderful quotes about creation and his love of the Lord can be found in any biography about him. Tragically, he died at a very young age due to abdominal cancer. He probably would have won numerous Nobel Prizes if Nobel Prizes were given during that particular century. He also was the one who put the mathematics behind the work that Michael Faraday did in investigating the relationship between electricity and magnetism and the resulting technologies of electric motors and electric generators. In any case, we want to make sure that we recognize the fact that though the speed of light is a constant in a vacuum, that would imply that the speed of light would be different in other media, such as air, or maybe a fiber optic cable, or some other material through which light could travel. And indeed, the speed of light is slightly slower in these other materials than it is through outer space. Frequency is named for Heinrich Hertz and is called the Hertz. 1 cycle per second, one up and down, 1 wavelength per second is called a Hertz. Now, maybe you listen to KMOX radio. KMOX radio broadcasts at 1120 on your AM dial. 1120 is a measurement of kilohertz. So it would actually be 1,120,000 hertz. If you listen to Joy FM, which is 99.1, it's the contemporary Christian music broadcasting station, FM radio is in the megahertz. You might also recognize these common prefixes. We use them for every third power of 10. So a million is the micrometer. Nano is for billion or billionth. Less familiar is the angstrom. It's an old-fashioned one that I used to teach several decades ago, but is not used as much anymore. But it was 10 to the minus 10th meter, and is designated with this letter A with a little circle at the top of it. You should also know that visible light is from 400 to 700 nanometers, generally speaking. And here's one of many, many different kinds of electromagnetic spectrums that you can find online and in textbooks. Please notice that the frequency and wavelength are inversely proportional. So as my frequency is getting smaller and smaller and smaller, the wavelength is getting bigger and bigger and bigger. The other thing that's very important to remember is that energy is proportional to the frequency. So therefore, you have your highest energy where you have your highest frequency. So this should make sense. Gamma rays photons of gamma rays pack so much energy, not only can they go right through your body, but they can go right through the earth. X-rays pack enough energy to go through flesh and skin and muscle, but cannot penetrate your bones. And therefore, an X-ray will leave behind a shadow of your bone on photographic film. Ultraviolet radiation packs enough energy to burn your skin or to increase the melanin in your skin to give you a suntan or a sunburn, but also is responsible for skin cancers, as yours truly is finding out. Then you have this narrow range in the middle to which human eyes are sensitive. We call that the visible spectrum. And one of the common ways to remember the order of the visible spectrum is to remember the name Roy, G, and then Biv, where Biv is blue, indigo, violet. Roy G. Biv, to remember the order of the visible colors. Notice, please, that ultraviolet is just beyond violet. And notice that infrared is just beyond red. Infrared radiation is often thought of as thermal heat and often is used to warm up your hamburgers at a fast food place. Now, beyond infrared, or we could say less energy than infrared, is going to be microwaves, which would also include radar. I've sometimes wondered if you put a small radar oven on the dashboard of your car, if that might not interfere with the radar gun if someone's trying to track your speed. But please don't do that. Then, smaller energy yet is TV and FM, and then you have your AM radio. Now, those cannot physically, of course, damage your skin, but they certainly can damage your heart and your brain depending upon the kind of stuff you're listening to and watching. But they can also be helpful as well. So please use your discretion as you use TV and radio. So a few other things in this breakdown. Radio waves are caused by charges that are accelerating through a conducting wire. Microwaves are short wavelength radio waves. So you can have short wave radio. My dad had a short wave radio that I could listen to. It wasn't one that I could broadcast on, but I could listen to that. And I remember one time listening to a wedding in the Netherlands when I was in grade school down to the shortwave radio in the basement. Radar is in the same vicinity as I mentioned earlier. And interestingly enough, microwaves cause water molecules to flip-flop. And the more the water molecules flip-flop, the more kinetic energy they have, and that translates into greater heat. So anything that has water somewhere in it can be warmed up in a microwave oven. Infrared waves is that radiation. Remember, we talked about three ways in which heat is transferred: conduction and convection and radiation. This is what we mean when we use the word radiation in that context, not to be confused with nuclear radiation. Then we have our visible light, which involves the rearrangement of electrons in atoms and molecules. And there's an awful lot that's been studied about the function of the eye and the retina in the back of the eye that responds to photons of light. And if you go into optometry or become an ophthalmologist, you would study that an awful lot. Ultraviolet light is responsible for suntans, but also sunburns and skin cancers. Fortunately, we have a lot of ozone, a rather large form of the oxygen atoms clustered together in groups of 3 instead of in like 2, O2 for oxygen that we breathe. And that's concentrated up in the stratosphere. And it really helps to absorb high energy ultraviolet radiation, which, if it was not doing that, would create all kinds of skin cancer problems. Not to mention being somewhat lethal to sensitive forms of flora and fauna that's very, very small. Sometimes you might read about concerns that the ozone layer fluctuates. It increases and it decreases, and you get a so-called hole in the ozone. And for a while we were concerned about the dissipation of the ozone because of the release of chlorofluorocarbons as propellants in aerosol cans. And so that's been banned, or most uses have been banned. Then we have X-rays. The acceleration of high-energy electrons cause X-rays to be emitted. It's kind of like the opposite of the photoelectric effect. Not only can high-energy light cause electrons to jump off a piece of metal, high-energy photons can cause those electrons to jump off a metal, but high-energy electrons can produce high-energy photons that are released from the metal. There was a small amount of X-rays produced in the Van de Graaff generator when we were playing with that. Gamma rays, of course, have a huge amount of energy and can be blocked by certain layers of lead, as you will learn when we get to our unit on nuclear physics. So if I can make a Venn diagram right here. In the Venn diagram here, we have all of our forms of electromagnetic radiation, including gamma. And in the right-hand circle, we're going to have our nuclear radiation, which would be alpha and beta and gamma. And so gamma is both a form of nuclear radiation when an unstable atom decays, but it is also a form of electromagnetic radiation. It's in common with both of these kinds of radiation. Interestingly enough, we can build different kinds of telescopes to look at every one of those different categories of electromagnetic radiation. So here you have a look at the Crab Nebula, which was first observed by the Chinese back in the year 1054. And of course, it began as an exploding star that suddenly showed up. And we can measure the rate of expansion because we know that it's been not quite 1,000 years since this event happened and was recorded. And we can measure the distance from the center to the outer reaches of this glowing gas to know the speed at which this nebula is moving outward. But you can see it takes on different forms under different kinds of electromagnetic radiation, and it reveals different types of information. Of special note might be the electromagnetic the X-ray image that we see here, because you can see this kind of circle right there with jets that seem to come out perpendicular to the plane of that circle. Now, the last thing I want to talk about, the Doppler effect. We mentioned this way back in October. In fact, we took a day of class and I had a special PowerPoint where we talked about the fact that just like sound has a Doppler effect, so does light, which means that when we pick up a red shift, the set of spectral lines that instead of being where they normally are when we observe them in the laboratory, are farther to the left or red side, I should say, of the spectrum. Same relative position to each other, but on the redder side, they have shifted to the red side. This tells us that the object producing that light, or those of us receiving that light, are moving farther apart from each other. If we see a blue shift, that means that the object producing the light, or the receptors of that light, are moving closer and closer together. And so here's that Doppler effect equation. Now, again, we keep in mind that we're not talking about relativity here, where your speed gets closer and closer to the speed of light. We're talking about the speed of the object producing the light being much, much less than the speed of light. And you can see that when you have a plus sign, 1 plus this fraction gives you a fraction that is greater than 1. And so your actual frequency multiplied by a fraction bigger than 1 gives you an observed frequency that is even larger. And that greater frequency is that red shift. Now, on the other hand, let me erase that. On the other hand, if we use the negative sign, you're going to have 1 minus a fraction. And so that's going to give you a fraction that is less than 1. So the actual frequency of the light that's being produced by the star or the nebula or whatever will be multiplying a fraction less than 1. And so the observed frequency is going to be less. So if the frequency is less, the wavelength is bigger. In any case, that's when we're going to be talking about a blue shift. So the positive sign is when the source and the observer are moving toward each other. And I don't know, I may have said that backwards. That's your blue shift. And then the negative sign, I think I did say it backwards, is going to produce a decrease. And that means the object is moving farther and farther away. And this cosmological red shift we see everywhere we look. There are a couple exceptions. If you have two binary stars that are orbiting each other, if both of these stars are orbiting each other, going around and around each other, and and we're looking at them, and let's say this is the Earth down here, this might be coming towards us and this star going away from us. We'd see a blue shift here and a red shift here. And then when this star gets around to the other side and this star gets around to the other side, then they swap. And then we get a red shift by the star that used to give the blue shift, and a blue shift by the star that gives the red shift. But even here, the net movement of this true binary combination is moving away from us. The other example is when you have a large galaxy. And if you have a very large galaxy with its spiral arms, if the galaxy is traveling away from us, even when that's happening, one end of the galaxy would be traveling towards us, the other end moving away from us as the galaxy is receding due to the expansion of the universe. And there are some Christian astronomers and astrophysicists who think that, and they make a very good case, that the numerous times in Scripture that where the psalmist or Job or the writer of Moses, the writer of the opening books of the Bible, talk about the stretching out of the heavens, it's actually a reference to the expansion of the universe. But of course, the bigger implication is that if the universe is expanding, so if I make a timeline, and this is in the future, and this is in the past, if the universe is expanding, that means if you go back in future, if you go back in the past, then it is contracting. And you keep going back and back and back until at one moment you have this point in space, infinitesimally small, containing all the energy of the universe and all the matter of the universe and all the information of the universe. And of course, where did that come from? The Big Bang, as this is sometimes called, The Big Bang talks about everything after that dot becomes this expanding universe with the distribution of mass and energy and information and organization. It doesn't explain where this original stuff came from in the first place, but it implies exactly what Genesis 1:1 says, that in the beginning, God created the heavens and the earth. And this, of course, is what has caused many astronomers and astrophysicists, and then other people who think about these things as well, to recognize that this universe had a beginning that is consistent with Genesis 1 in the Bible, regardless of how much you want to argue about when this occurred. And so you either accept what the Bible has said all along, or maybe you try to do an end run around that because your worldview does not want to go in the direction of there being a God, and therefore us needing to obey that God. And so they might invent things like a multiverse instead of a universe, which, like we said way back in October, isn't even technically a scientific theory because there's no way to test this. Anything that we can detect or measure is part of this universe. But of course, from a Christian perspective, God can make as many universes as he wants. And this only exacerbates the problem for those people trying to do an end run around the existence and the eternality of God. And that is that now you have to come up with a mechanism that can generate universes. And who made, or where did that mechanism that can generate an infinite number of universes come from? And I'll leave you to ponder that question.